तो सबसे पहले व्हाट इज़ द definition of turbulence. Okay, now I will go a little bit faster because everything is covered. In turbulent flow, velocities along with all other properties of a parcel of fluid vary in random and chaotic way. So not only velocity, other properties also vary randomly. Okay, and we are talking about a parcel of a fluid. So there is a difference between a molecule and a parcel. Okay, parcel is basically a group of molecules, right? So it's, you can say, like a drop. You can even say it's a drop. So the molecules are in any way random, they are chaotic, but droplets are not. Normally in a laminar flow, you can't find a drop which is going, or a part of the fluid going in a chaotic way, but in random flow that happens. Okay. So again it is here, however the turbulence is not measured at molecular level, it is defined for an agglomerate of molecules, drops or parcel of a fluid. Same thing we are talking about. Okay, and this is represented like this. We have talked about this. U, we are talking about U here is equal to U bar plus U prime. Okay, and this thing is U prime, we have talked about it, and this value is U bar. Okay. And this is our U actual value. Okay. Now there are two things that lead to start of turbulence and its sustenance and continuous. So there are two things. Now one is the disturbance in the flow. The second is the property of the fluid to dissipate the disturbance. So there are two mutual forces which are working. One is the kinetic energy and the second is viscosity. We talked about it. It's a kinetic energy which leads to turbulence, which initiates turbulence. Of course, it's not only kinetic energy, it is the disturbance, or you can say any structure which is which may cause the turbulence, right? But what does sustain it? Viscosity. If the viscosity is less, it will be there for a longer time. If viscosity is more, it will vanish quickly. Okay. Then we have talked about sources of disturbance. There are three sources. We have talked about it. One is the free surface, right? So now the reason for that is, we have talked about that at the free surface molecules are relatively free because they are bound only on the one side. Okay. Then surface roughness is the second, and sudden change in boundaries. We have talked about all of them. So you can look at the previous lectures for details. Now when this disturbance is amplified and sustains itself, it leads to turbulence. So there is a generation of disturbance and there is a amplification or sustenance of the turbulence, and the third is dissipation. Okay. So when as we have discussed, that turbulence starts from deterministic structures, right? So those structures are not random, like the surface roughness or the change in surface, right? Or free surface, they are not random, they are defined. Okay, but still they lead to turbulence, they lead to some disturbance which actually amplifies. So then it leads to turbulence. Now, what is the sustenance of turbulence? We talked about it, that at low Reynolds number, inertia forces are smaller than the viscous forces. So what will happen? As a result, naturally occurring disturbances don't grow. So if the kinetic energy is small, Reynolds number is small, those disturbances do not grow and they dissipate along with the flow, and the flow remains laminar. Okay, it's not that there is no disturbance in laminar flow, but it is small and it is taken care of. Okay. At high Reynolds numbers, inertia forces dominate and leads to disturbances that sustain themselves through eddies. Now what happens is, once a disturbance is created and viscous forces are less, that disturbance sustains itself through eddies. Now what are these turbulent eddies? So rotating flow structures that sustain themselves due to angular momentum are called turbulent eddies. So it's basically whirling motions, right? Now this type of fluid motion, actually what happens is, because of angular momentum, this sustains itself. Okay, so that vortices actually sustain themselves, and that is called turbulent eddies. Now then they have a wide range of length and velocity scales. Now what does that mean? That it's not that only one size there. You have a large eddies, right? You have smaller eddies. Okay. You have one which are going slow, and there are others which are going faster. So their speed may be different, their sizes may also be different. Okay, so that is why length and velocity. The largest eddies have characteristic velocity and characteristic length of the same order as velocity and length of the scale of mean flow. So what will be generally the largest eddy? That will depend upon the velocity of the flow and the dimension of the domain. That determines. Eddies cannot be bigger than the domain size, right? So basically that determines. Now what happens is, these large eddies, when UL is greater than nu, that is mean flow velocity into characteristic length, is greater than viscosity, that means inertia effects are greater than viscous effect, same thing, and this is nothing but telling you about Reynolds number. Reynolds number is high, then large eddies are formed. The largest eddies are dominated by inertia forces rather than viscous effects. They are effectively inviscid and do not dissolve with time. Okay. Larger the eddy, UL is larger than nu. So it will sustain itself for a longer time. Now then there is something called vortex stretching. We have talked about it. However, the presence of velocity gradients. Now what does that mean? You have a now velocity gradient is that you have a velocity here, right, different in velocity as you are going y direction. Now if a eddy is entrapped in this, what will happen? This will lead to eddy stretching. Okay, this is what actually happens. Now, however, the presence of velocity gradient in the mean flow causes stretching of eddies that are appropriately aligned by forcing one end of the eddies to move faster than the other. So what happens is they start moving, one end is moving faster than the other. During vortex stretching, the angular momentum is conserved. Now angular momentum will remain conserved. So the stretching work done by the mean flow on the large eddy provide energy that maintains the turbulence. Now this stretching also imparts energy to the eddies. Now then what happens, that these larger eddies generate smaller eddies due to vortex stretching, right? So what happens here is, you have an eddy like this, it stretches like this, then it breaks into two. This is what happens. Finally it becomes unstable and it breaks into. So what is happening is now this process continues until the eddies become so small. So this process continues until the eddies become so small that viscous effects become important. The energy associated with the smaller eddies is dissipated into thermal or internal energy due to viscous forces. So what happens, slowly and slowly these eddies get reduced in size. Now what happens, the velocity is smaller, viscous forces are more, and those slowly dissolve into the flow, right? So then there is something term called energy cascade. Energy cascade is nothing but larger eddies breaking into smaller eddies. So continual transfer of energy from larger eddies to smaller and still smaller eddies is termed as energy cascade. So what is happening is, energy of the bigger vortices is being transferred to the smaller one, slowly and slowly. Not that they actually transfer, what is happening is the bigger one are generated, right? They keep on generating and they keep on getting divided into smaller ones. So they basically in a way sustaining that. It's not the energy is transferring, it's basically the bigger one are breaking and creating the smaller one. So in a way you can say the energy is transferred from the bigger one to the smaller one. Now this is something about turbulence from a book which is called, author is Ferziger and Perick. So now he is talking about the properties of the turbulent flow. Now first thing we should know that most flows encountered in engineering practice are turbulent. This is what I was saying right from the beginning, that most of the time you will encounter turbulence, and I extended it to say that is why you cannot forego turbulence. You have to study turbulence. There is no escape from it. Okay. Then it says that turbulent flows are highly unsteady. That is true. They are changing with time. They are three-dimensional. So although we are basically making them in two-dimensional, showing them vertices as two-dimensional, but this variation is in three-dimension. They can be moving in any direction. So what it is saying, that instantaneous velocities, the fluctuating component of velocity fluctuate rapidly in spatial dimension. As I told you, there are two components. what he is talking about is that u is equal to u bar plus u prime. Now this is the average component. It may be in 2 dimension, but this variation is in 3D. So the fluctuation in all the directions. Now what is the cause of fluctuation? Cause of fluctuation is microscopic structure of the fluid, right? It's like that if you drop a glass, how it will break, that is not in your control, right? Now what is actually happening is, even if you hit at the same point with the same force, the cracks in 2 different pieces will be different, because the inner microstructure is different. How the crack will propagate will depend upon the existing structure of the fluid. Similarly, in a fluid, how the random velocity, the fluctuating velocity will come in is actually governed by the microstructure, how the atoms are connected to each other, right? And which is varying from time to time. Even when you are seeing that the same flow is going, same type of flow is going, internally what is happening is entirely different, right? So this is what you should appreciate. They contain a great deal of vorticity. Indeed, vortex stretching is one of the principal mechanisms by which intensity of turbulence is increased. So I couldn't make out what it actually means is, but it appears that the turbulence is increased, it spreads and increased because of vortex stretching. Because unless until vortex stretching is there, it will not form smaller vertices and it will not distribute. Once there are smaller vertices, then now they can spread anywhere, right? So the whole flow will become turbulent. So you are starting from a point where the large vertices are generated, right? And you will find that where the large vertices are generated, that is a localized region. But after certain time, the whole flow is turbulent, and that appears in the, which we shown the first 2-3 slides, in which when the vertices were formed, at that point they had a fixed structure, but afterwards they break away and mix. Now then it is very important that why turbulence becomes important. Turbulence increases the rate at which the conserved quantities are stirred or mixed, and the final mixing at the molecular level is accomplished by diffusion. So there is 2 types of mixing taking place, right? One is the mixing in a, you can say, at the parcel level, right? And the second is a mixing at a molecular level. Now I give you an example. You are spraying water on your garden, right? Let us say it's a there is no trees there, no grass there, only earth is there, clean earth is there. You sprayed water. Now what is happening? Water droplets are falling everywhere. Now then these droplets, where they form, after some time what will happen? They will start seeping all around. The water will start. So even when a particular point the water has not dropped, it will become wet after some time, because molecular seeping will start. So this is called molecular diffusion. So one is that you are distributing, that is you are mixing, right? And the second is you are Even if you take, let us say, you can take example, let me say, okay, you can even take like this. You have a tub of water here, okay, and I have some dye or some chemical. What I can do, I can drop it like this. So what has happened? Or you can say you have a fertilizer or something you spray like this, put that in there. Now in that water, what will happen? These particles have, or you can say the drops or the particles have dropped at different places. Now when they go down, they start diffusing and they mix up the whole thing. Finally you will find after some time there is no particle which you have thrown. It has mixed. Everything is mixed. So that is the difference between the two. One is the you have a mixing at the macroscopic level. One is at the microscopic, at the this. So this process is all called turbulent diffusion. When you are mixing in, it's something like when you are mixing in terms of particles, right? Parcels of the particle. That is turbulent diffusion. And mixing at the molecular level, the final mixing is at the molecular level. Now, what is the result of that? That both mixing and heat transfer may be increased by order of magnitude due to turbulence. Right? Now, with the turbulence, what happens when you are spreading it all around? Your mixing becomes very fast. Again, take the example of soaking the earth, watering the earth. If you leave water at one point, right, water reaching all the area will take a lot of time. You are putting water only at one point. It will take slowly and slowly, it will get distributed all over. But if you are spraying it, then you can cover the larger portion quickly. Then what is happening is your mixing is happening 10 times or 100 times faster. That is why you put sprinkler. Earlier what they used to do in agriculture, what they used to do, they used to make small canals, put water there, and that water goes there, and then there are branches and water goes there, and finally it fills the, so wherever water is going, that it will first soak that place and then it will go onward. Okay, that type of watering is very slow. Moreover, there is a high concentration at the beginning, and at the end there is a low concentration. But if you just spraying, then what happens? Your mixing is very fast, right, and uniform. So that is what it is talking about. Same thing happens in case of heat transfer as well as mixing of species, different species particles. It happens. Okay. Now then it says that turbulent flows contain both deterministic and random events. The coherent structure that are repeatable and essentially deterministic are responsible for a large part of the mixing. Okay, the repeatable and deterministic structure are those that originate from fixed causes. So same thing we have talked about, that there are places from where the turbulence starts. They are repeatable. These are the deterministic structures, are the ones that from where the turbulence originates. As the source of disturbance is fixed, the disturbance itself is deterministic. So what you are saying is that your disturbance is deterministic. You know a lot about that disturbance, how it is, what is the velocity, how it is starting. You can find out, and you'll find that it is in a fixed range it moves. Suppose there is a vertices which is starting. At the starting point, you will know that what is its angular velocity and what is its size. You can make out. But however, as these structures move on and dissipate, they pick up randomness, because dissipation is a random phenomenon. We have talked about it. Okay. It is the random nature of flow structures that differ from each other in size, strength, and time interval. Now, all these variations, as the larger vertices start breaking into smaller and smaller, the randomness keeps on increasing. Okay? And that makes the study of them very difficult. Then it says that turbulent flows fluctuate on a broad scale of length and time scales. Their sizes are different, their angular velocities are different. This property makes direct numerical simulation of turbulent flows very difficult. So we have talked about it. And now effects produced by turbulence may or may not be desirable, depending upon what is our objective. If we are looking for heat transfer, we are looking for mixing of chemicals, then the turbulence is desirable. We create turbulence. But when it is a question of a flow, moving fluid from one place to another place, turbulence is undesirable because you have to do more work. Your viscous losses increase and you have to put more energy to flow. It's better that the flow is non-turbulent or laminar. Okay. So it depends. Sometimes you may want it, sometimes you may not want it. Again, the increased pressure drop or the heat transfer by an order of magnitude is not unusual. And then second thing to be noted is that the rate of heat transfer and pressure drop, they are not slightly different from laminar flow. 10%, 15%, like that. They by an order of magnitude, they are significantly different. Right? Which we come back to the same thing, that now that turbulent flows cannot be approximated by laminar flow. There is a significant difference between them. Okay? In fact, issues concerning turbulence, we have talked about this, that most of the real situations involve turbulence. Okay. Then we have also said this, the fluid behavior of turbulent flow is much different than the laminar flow. Okay. Then we talk about scale of turbulence, and I gave you an example that if you have a region of 1 meter, 0.1 meter by 0.1 meter and the high Reynolds number, then your eddies can be as small as this 100 micrometer, and you may need points up to grid points up to 10 raised to power 9 to 10 raised to 12, which means 10 raised to power 9 is a million. Yeah, 10 raised to power 9 means 1 billion, that is 1000 million, and this would be 1000 billion. And then we have said that you will have to break time steps into 100 microseconds if you have a frequency of 10 kilohertz. Now again, which means that it is not possible. Okay, it becomes very, very small. You require a very high capacity of computer. Now what is this law of turbulence? This is also important. Okay. Now what are we saying? That we have no equations to predict the random fluctuation in velocity and other flow parameters which are caused by surface roughness, microscopic features of the surfaces, or microscopic behavior of the fluid. Now why this randomness is coming is because of surface roughness or the microstructure of the fluid. Okay, and there are no equations available to predict that. Okay, we cannot study those microstructures. Even if we study them, there is a limit to which we can go, and if we go, then that much data cannot be included, because okay, right? And that is why we have talked about this problem also, that what is the solution available. So turbulent flow, we have no such law which can help us solve the problem, right? Which can predict that what is happening. We need to know, because what basically we need to know? We need to know that what velocities are there. Okay. And subsequently what is the temperature, what is the pressure. Now we are not able to know because it becomes a random flow. So another solution available to us is that to reduce the size of the grid. And this is also important, that if you take this case, right, if your cell size is greater than the size of the vortex, then for you the velocity is 0, because your v is actually an average velocity of the flow. So if you need one velocity to define this cell, it is 0. So another option available to you is to break into 4 parts, and if it's 3D, you break into 8 parts, and now you have 4 velocities to define the flow. You are closer to the reality, right? And that is why you have to go to smaller and smaller size of the thing. Okay. So now this thing, which means that if you are going smaller and smaller, your grid size will become bigger and bigger, and it is unmanageable for very large and unmanageable on current computer. So this thing cannot be done. So we go for time averaging. Okay, we have talked about this, and that is called RANS. Okay, and now when you are doing time averaging, what is happening is you come across term, they are called Reynolds stresses. Okay, now we have no laws available to account for Reynolds stresses. These are 9 variables which are random variables. You don't know anything about them. You have no law to predict them, right? So it becomes a problem, open-ended problem, instead of a closed-ended problem where number of equations and number of unknowns are known. This becomes an open-ended problem where number of knowns and unknowns are much more than the number of equations. Okay. Now then we have to make approximation. As a result, some empirical equations are generated. Now you know that RANS we have adopted, but the moment we have adopted RANS, we have to now develop equations, because we are encountering 9 unknowns. So we have to have equations for them, and we don't have any theory for them. Those are random variables. random fluctuations. So what we do, we basically make empirical equations for them. What does that mean? Empirical equations are based on your experience and theory. It's a mix of theory and experience, but it is not 100% theory, right? So it depends upon the type of flow and your understanding and your approximation, etc., etc. So these approximation introduce an element of uncertainty. So here you get that uncertainty comes in. The moment you are talking about a model, it is an empirical model. It is an approximations, right? And there are number of models. You choose one of them, right? If it was, you can say, theoretically possible to define the randomness, you could have developed one model, one equation, one set of equation, and the computer would select whichever equation. Maybe even if there are 10 different equations, one applied here, one applied here, वो स्टेप्ड फंक्शन आप जानते हैं ना, तो एक केस में कुछ फंक्शन लग रहा है, एक में कुछ लग रहा है, एक, इवन इफ दैट इज डिफाइंड एंड इफ यू नो द फंक्शन यू कैन स्विच from case to case, right? But the problem here is we do not know any case, we are not sure about it. Those empirical equations are not 100% correct. So this is the so this problem is solved to an extent by validating the CFD formulation for the specific problem with known solution. So here what we talk about validation. Okay, so that is why validation becomes very important. Whenever you will be solving a problem of CFD, people will ask what is the validation, and in validation what you are doing, you are solving a known problem with the model you have adopted and saying that my solution with this set of problem is almost as per the actual problem, experimental data, which means now I can extend it to the other problem. So basically what I am saying, I am making a small jump, that my model is good for this particular case, right? Now the second case is slightly different from this, so I assume that whatever I am doing here will be applicable there also. And that is why validation becomes important, because you never know that what is the real equation for that particular case which you are talking about. तो ये तो जो है, this is what we have given a brief summary of what the turbulence is. It's almost a repetition, except that we have covered some points which were not there. I think most of the points were there. Now in the next class we'll be talking about these equations, and in these equations basically again we will be just doing the mathematics of it, and I'll see if I can pass on this mathematics to you with a simple mathematics, so we can so what I am talking about now is another 2 minutes I will take. What I have told you, that you require models, right, to solve a problem, and which model is good or bad or which is suitable here, that you have to decide. That depends upon the experience and what the people have done before. Now we will just give a slight insight into how a model is developed. Okay, that is the only thing, and that we are talking about K epsilon model. Okay, even this description will be very, very superficial. just to expose before you that the complexity of these models. And then there are number of models like this, 7 or 8 or maybe even more, and each has its own mathematics, and that mathematics is real tough. Okay? But we are not going into it. We will be using the models directly, but some insight I will give you into K epsilon model, which I found is the simplest one from the mathematical point of view. ठीक है? तो and then at the end of it we will be talking about what is turbulent viscosity, turbulent kinetic energy. Those things will come. And okay, so we stop here. Okay.